So in these problems, we'll be using geometry to model functions. So with a lot of these, we'll be kind of reviewing the different geometry functions we should know by now, all their different formulas. We'll get some practice with them, and then applying them to this function notation. So we can end up with this model that we could use and plug in different values based on different scenarios. Alright, so with each of these problems, I'll be drawing from different formulas and giving us a little bit of review. So in this first one, we have the diagonal of a square. So I'm going to draw a square the best that I can. So a square has all the same side lengths. So we're calling the side length S. So it's that I have these 4 side lengths that are the same. And then we want to look at the diagonal, which is L. So we want to express that length L of the diagonal of a square as a function of its side length. So what we want to create by the end of this is calculation for length given some side lengths. So we want L of S for our final function here. So what I have here is I have some right angles. So I have this triangle that I'm working with where I have the 3 side lengths and it's a right triangle. So this is going to use the Pythagorean Theorem, which, as a refresher, means that if we have a right triangle with side lengths A, B, and C, where C is the hypotenuse, then C squared equals A squared plus B squared. So for our triangle, L is the hypotenuse. So the hypotenuse is the longest side, or you can think of it as the side length that's opposite the 90-degree angle. So what that means is we'll have the hypotenuse squared, so L squared equals, and then the sum of the side length squared. So S squared plus S squared, which now we'll just simplify. So L squared equals 2S squared. And then we'll go ahead and take the square root of both sides so that we solve for L. So square root of a square just gives us that variable, so we'll just have L equals. And then when we take the square root of both sides, we typically have plus or minus, but with word problems, the negative usually doesn't make sense. In this case, having a negative length doesn't work. So only in these cases, we'll skip the plus or minus, we're just going to use the positive. Now, square root of 2 will be stuck, but we can take the square root of S squared, and that would give us S. So we can take S out of the square root, but we'll still have a square root 2 stuck in there. So with that, we kind of used a geometry rule to get a setup going, and then to get to our function notation, which is our next step after this, it's all about solving for that variable that we want to create a function for. So that I have my variable that I would solve for, and then that input variable is on the other side of the equation. So my function would be L of S equals S times the square root of 2. Okay. Our next one, we're going to have an equilateral triangle. So this is a triangle with all the same side lengths. And we're calling the side length S. So we have 3 side lengths of S. And we want A for area. So we want to find this function that calculates area given side length. So we want to find this A of S. So area of a triangle. Area equals 1/2 times the base times the height. So what we're going to need is the height here, which goes from the vertex and creates a perpendicular with the other side. So that would be our height. And then we actually know our base. Our base is the side length S. So really I can take this one step further. This is going to be 1/2 times S times height. But what I want to do is when I have my function, I want S to be my only input. So this H is causing issues. So I need to find another way to represent h, and especially I would like to find a way to represent it so that it's only in terms of s. So what I can do is similar to the last example and recognize that I have this right triangle here. So I have side length h, side length s, and then this side length down below here, which this total distance is s. So what we did with h, by dropping that perpendicular, it took half of s. So my three side lengths for the triangle, h, s, and half of s. So what I'm going to do is use the Pythagorean Theorem so I can solve for h. And as I can see, all of my other variables, my only other variable will be s, so this will work out great. So the hypotenuse is opposite of the 90-degree angle, so s is my hypotenuse, so we'll take hypotenuse squared equals, and then h squared plus 1/2 s squared. And in parentheses, we want that whole side length squared. And now we're going to simplify, and we'll have some fractions to work with here, so we'll get a little review with that. So s squared equals h squared plus 1/2 squared is 1/4, so half times a half, and then s squared. I want to solve for h, so what I'm going to do is subtract that 1/4 s squared from both sides. So what that will give me is h squared equals s squared minus 1/4 s squared. Now, these two values are like terms. They have the same variable, they have the same exponents. So what I can do, imagine, is this is 1s squared, and then I have minus 1/4 s squared. So what we would do is you combine the numerical coefficients, so 1 minus 1/4, which is 3/4, and then our like term, which is s squared. Alright, and that's as far as we can simplify it until we take our square root of both sides. So again, we'll only have the positive because we can't have a negative height. So what we're going to have is h equals, and then square root of 3 is going to be stuck. So I'm going to think about this in pieces. So square root of 3, denominator is square root of 4, which the square root of 4 is 2. Square root of s squared is just s. So with that, we have our area formula. We had to use some Pythagorean theorems so that we could get our variable all in terms of s. We had a little bit of fraction work to do there, but not too bad. And then with your square root, since this is all multiplication and division in here, you can just take the square root of the individual pieces so that you can simplify it down. Alright, so all of this was to get an area formula where our only input is s. So I'm going to go back to where I have 1/2 base times height, but we know that the base is s, and I just need to substitute in for h right there. So I'm going to have 1/2 times s times, and then height, which is root 3 over 2 times s. And then I just have one more step to simplify here. So my fractions, 1 times root 3 is just root 3 over 2 times 2, which is 4. And then s times s is s squared. You might have ended up with a different format here, like maybe you had root 3 s squared over 4, or maybe even s squared root 3 over 4, that's even better. All of those are going to be the same. Just be cautious of this format here, root 3 times s squared, and make sure your radical doesn't wander too far. Sometimes with the root at the beginning, it can go too far and capture more than is actually included. Alright, some more examples, because that's the best thing we can do with word problems, is look at as many cases as we possibly can. So, what we have here is the graph of 4 minus x squared. That's our parabola there. And then we're looking at this box that's trapped by that parabola, meaning we're going to have these pieces on the x and y axes, and then one coordinate's going to come from our parabola right there. So if we have this xy coordinate, x is giving this distance right here, and y is giving this distance. So if we're looking at area of a rectangle, we'd want our width times length. But in terms of width times length, we're using x times y. So what we could do is think about this area of the rectangle is coming from x times y. However, if we want to express area of the rectangle as a function of x, then I want to find a way to replace that value of y so that it's in terms of x. I don't want two variables in there, I just want that one variable, x. So what we can do is use the fact that this value for y is coming from this expression 4 minus x squared. So what I'm going to do is substitute in for y this 4 minus x squared. So where we have x times y, that's the same thing as x times 4 minus x squared. And then I'm just going to distribute it so it's a little simpler. So 4x minus x cubed, and that would do it. Thinking about a domain, so domains in terms of x, so we want to think about how do we want to limit our x values. So what should happen is we'll be limited by 0. We wouldn't want x to be 0 because there wouldn't be area then. So we're going to start at 0, and it kind of depends on whether or not you want to include 0. I'm not going to include 0 because then you wouldn't technically have a rectangle, you would just have a line. But some might argue that you could include 0 because then you'd have an area of 0, but then the rectangle doesn't exist. So I'm not going to include 0, but we'll go right up to 0. And then we could think about, well, what's the largest rectangle we could have? And the idea would be of when y is 0, when this stretches so far that it's along the x-axis. So we could do this a few ways. How I'll show you both ways, algebraically and with the graphing calculator. The graphing calculator will be fast because we're just going to graph this 4x minus x cubed. So we're going to graph our function that shows area. So the output of this function is showing area, which really we just want to focus on this little bit in the first quadrant. Because when we're below the x-axis, that's showing negative area, and we can't have negative area. So we're going to focus on over here where we have positive x values. So we have positive x coordinates coming through, and then this red line is representing the area of our rectangle. What we can see is that area starts at 0, but we don't really want to include 0. And then it could go all the way up to x equals 2. But then it goes into negative area, and we don't want that. And again, we won't include 2 because it's really just a straight line and not really a rectangle, so it wouldn't have any area to it. So I'm going to say 0, 2. Now how we could have solved this algebraically is plugging in 0 for a of x and solving. So what we would have is take out our greatest common factor, which would be x, and then we would solve. So we'd have x equals 0, we would have 4 minus x squared equals 0, and then we could solve, and we'd end up with x equals plus or minus 2. However, we can't have a negative 2 here because we're stuck in the first quadrant, so really we have the positive 2. So solving algebraically, we can see the limitations of our x values there, and then just understanding how we want to include those endpoints. Alright, one more example here. We are going to have a page, and there's going to be a printed area and then margins. So I'm going to draw us a picture over here. So we're going to have a page, and on this page there's going to be an area where you can print things. Let's see if I can move that just a little bit. All right. So this page we have height and width. So I'm going to call this H and this W. And then we have margins on the paper. So at the top and bottom, there are 1.5 inch margins, 1.5 inch. And on the sides, 1 inch, 1 inch. So we can see that the area of the printed region is 48. So what that would tell us is that if we take H times W, that should be 48. It's the area of that rectangle. What I want is to express height as a function of width. So I want to find this H of W. So what I'm going to do is solve for H here by dividing both sides by W. So I'd have H of W equals 48 divided by W. Now let's talk about area of the entire page. So what we're going to do is add the margins. So if I think about this overall width of the paper, really I have 1 inch plus W plus 1 inch. So the width of the paper is really that W plus 2 inches. And then for the height of the page, I have this 1.5 inches plus H plus 1.5 inches. So for the height, I really have H plus 1.5 plus 1.5, which is 3. So for area, we would take height times width, but now our height is H plus 3, and then times width, which is now W plus 2. And I'm going to FOIL this out. So I'm going to multiply the first outer, inner, and last. So what that'll give me is H times W plus 2 times H plus 3 times W plus 3 times 2, which is 6. So I want area as a function of W. So I don't really want to see H in here anymore. I can see H popping up there and there. So what I want to do is substitute in that 48 over W, because those are the same thing. So for A of W, what I'm going to do is where I had H, I'll put in 48 over W, and then that's multiplying with W, plus 2 times H, but instead of H, I'll have 48 over W, and then I have plus 3W plus 6. And now I'm just going to simplify. So that first term, the W's will cancel out. So that's really just 48. And then plus 2 times 48 is 96. And that W will stay in the denominator. Plus 3W plus 6. And the very last step is that I can add that 48 and 6 together. So this area in terms of width will be 96 over W plus 3W plus 48 plus 6, which is 54. So, some area formulas in there, Pythagorean Theorem, using the graph as a coordinate, so some different scenarios, but it's all problem solving so that we can get to these functions in terms of a single variable. If you end up at a spot where you have multiple variables, see if you have a way of substituting in, like with this last example where I had H and W in there, just looking back to a relationship where you can make some substitutions.